Let's do binary tree level order traversal next. Given the root of a binary tree, return the level order traversal of its nodes values from left to right, level by level. So as an example, they want you to return 3 as the first level, and then 9 and then 20 as the second level, and then 15 and 7 as the next level. So there's a couple of concepts to keep in mind here. The first is, what is a tree? What is a binary tree? Well, it's a tree with at most 2 children per node. And then level order traversal, that's basically breadth first search with a little bit of a difference to make sure you're keeping track of how big each frontier is. So if you're doing a normal graph where it's not necessarily a tree, frontiers say like, okay, if you started at 20, the first frontier is 20, the second frontier is 3, 15, 7, and then the next frontier out would be just 9. That would be like breadth first search, frontier-wise traversal on a normal graph. But since it's a tree, we're starting at 3, and then this level down, and then this is the next frontier. So in C++, and probably in most other languages too, you're gonna want to use either a queue or a double-ended queue. And I'll talk a bit about the differences. A double-ended queue, you can add things to the front or back. And in C++, it also lets you do random access within anywhere in the middle. Versus on a regular queue, it's the same as a queue but worse. It has just functionality stripped out, so that would make more sense if you're doing like a group kind of, if you're working with other people and you want to reduce the chances of accidents and saying we're just going to use a regular queue. It has everything we need. We don't want all the extra stuff a double-ended queue has, and we don't want it available so that we don't accidentally use it wrong. That's all that is. A double-ended queue actually has really, really low overhead in C++. Um, it's a little bit of a lower level API, and yeah, so that's all I'll say about that. So we're gonna need a couple of things. First, let's declare the return variable. It's a vector of vectors, vector of integers. Ret for return, and I'm gonna check for edge case first. So if the root is null, and since the trigger for that is a pointer. If you have a pointer input, you generally want to check if it's in. Well, it's hard to check for every kind of invalid, but in interviews they definitely want to see you check if it's null. I've had that come up in like a Google interview before. I got through pretty much all the problems, solved it, and then you're like, oh, you got this pointer. Should you worry about what that can be? And I was like, oh yeah, you're right, that could be null. So he had to prompt me for that. I had done well enough on like the rest of it and gotten it on his good side. He also reminded me of to use a volatile keyword, which I'm not going to describe that here, but it was an embedded SWE interview, so volatile is something that might come in handy in that case. Um, so check for the edge case if an input pointer is null. And then we're also going to need another return statement here at the very end. And then we do all the work here in this part. For breadth first search, you generally want to do it with, there's 2 loops. There's a main outer loop, so as long as the queue isn't empty. And let me go ahead and declare the queue now. So it's a double DQ, and it's going to be of tree node pointers. Call it Q for Q. And we'll go ahead and add our root to the front of it. So Q.push back root. Double-ended queue also has stuff like push back. It also has push front, and similarly, it has pop back and pop front. That's what makes it double-ended. But I don't need those here. I'm going to use standard pushing to the back of it and then popping from the front, and that's just like the most conventional options. It doesn't super matter as long as you're accessing inputting to one end and polling from the other. But so we're gonna need. I'm gonna use a little bit of an unconventional form of the for loop. So in C++, the for loop is it's a superset of the while loop. So the only difference I'm doing is I want to declare a variable that's in scope only during the loop. I'm gonna call it node, just for whatever our current node is. And then, so yeah, so this first, before the semicolon, is just declaring variables. The second thing after the semicolon is the while condition. This loop will continue until this condition is no longer true. So while the queue is not empty. And then I'm not going to do anything in this third section, which would be, it would run it immediately after the end of each iteration of the loop. And usually people do that to update, whatever loop variable they're using, but I'm not going to do anything there. So this is while not empty, and at the very beginning of the loop, we call this and declare this variable, and it will go out of scope when the loop ends. What else are we gonna do? I'm gonna declare, so there's a regular vector here, and it's of integers. It's of, I'm gonna call it level. This is where I'm gonna put temporary variables, not temporary variables, temporary values. So every time we're traversing a level, um, we're going to add at each iteration of that stuff to this level, and at the end of that, we're going to add that to our output. I'm not normally a fan of declaring arrays inside of loops, but I don't really see a better way. I don't see any advantages not doing that here, because I'm going to have to clear this list every single new level anyway, so there's not really any point. Um, but I am going to add this begins to be where, let me just show you. So q.size. You set we at the beginning of each iteration of this outer while loop, the for loop, but it's really, think of it as a while loop. We know the size of the next level because everything in the queue at that time belongs to the next level. At the very beginning, it's just the root. So our first level is size of 1. And then we go through everything in that level and we add its children. We know its children are immediately in the next level. So once we're done with that, everything that's in the queue at that time would then be the entire next frontier. So this size matters. And then we're going to do an actual for loop. So this has to be a for loop. It can't be. This isn't like a sugary while loop like the one above. This one is an actual honest to goodness for loop. And it's going to be that way in every language you use. So I equals 0. I is less than level.size. Yeah, an honest to goodness for loop. And note that I'm using level.size, not queue.size, because the queue is going to shrink as we pop things off of it. But the level is not, at least at this, for the during the scope of this for loop, it's not. So level.I equals, what does it equal? I want to pop something off the front of the queue. So node equals queue.front, and then queue.popFront. Yeah, so this just reads it. This returns null, so you have to call it separately. And then I'm gonna put that node val. How do I know val? So tree nodes, as LeetCode describes them, defines them, has these 3 fields, integer, and then 2 pointers for the left and right children. And then these are some constructor definitions, but I don't care about these because I'm not using any of them. I'm using these 3 things here: value, left child, right child. So we get our output and we save it to our temporary vector. And then now we need to add children. For frontier-wise breadth first search, like we're doing in this case, level-wise as the problem uses the terminology of levels instead of frontiers. You do have to check if it's null first before putting it in. Now, normally I would be kind of an advocate of when, immediately, so when you pop this node off the queue, check if it's null before doing anything with it. But since we do need to know the size of the level, we have to check before putting it on because we don't want to put children. So for example, this level 2 here, its size is 2. Its size is not well, okay, that would always be 2. But this bottom row here, its size is also 2. It's not 4, even though 9 has 2 null children. So if we put nulls onto the queue, its size is going to be 4 when we want it to be 2. So we have to check first. So if node left q dot push back node left. And then same for the right. If node right q dot push back node right. And then why are we doing the left child first? Because it told us to. It told us left to right. So we have to do left first. And then lastly, after we finish traversing a single whole level, we want to add that to our actual output. So ret.pushback, push back level. And then when that's all said and done, we return. So I'm going to talk about runtime and do an example. It's breadth first search, which is normally O of, let's say, n plus m, which is the same as you also see syntax of v, O of v plus e. So that would be vertices and edges, where v is the set of vertices, so you use these bars to mean the size of the set of vertices. And then same for e. E is the set of edges, so then the bar means the size of the set of edges. And you'll also see n plus m, just kind of, that's just like convention. You'll see that a lot. But since this is, and then I'll also mention space complex. So this is time for BFS. And then space for BFS is also normally the same. But all right, so since this is a tree, we can simplify this time and space complexity down a bit. So space complexity would also normally be linear, potentially maybe just this, since you're only putting vertices. The number of edges is always going to be less than or equal to the number of nodes. So we can simplify this because the V is always going to dominate. So it's specifically because it's a tree. So BFS on a tree. The tree means the tree is what lets us simplify down from what it would be the normal runtime for a generic graph. Space for the queue. It's a double-ended queue, but same difference for space. We could potentially have, for example, the input is just 3. Well, we have 3 on the space complexity of the queue. We could potentially have the entire input on our queue in some hypothetical scenario where it's size 1. So that's our space complexity. It is linear. Yeah, realistically, you could, yeah. Every subsequent level, it could grow. So maybe the next second level, max is 2, max is 4. That tends to dominate. So you basically can have the whole thing on the queue. It's linear space. And yeah, this is a pretty fundamental algorithm. It's used in a lot of cases. It actually does come up in a few other things. Uh, let's step through an example. Go ahead and use this one then. Uh, so we've got our return vector. We check an edge case for the null pointer, declare our queue, put our root onto the queue. So let's say queue is this. And then we're going to have level, so queue, level. And do I need anything else? Not necessarily. All right, so first thing on the queue is our 3. And then for Gino, while it's not, so our queue is not empty, so we'll go ahead and continue. Level is gonna have one thing in it. So what is it? For I equals 0, I is less than 1, so 1 iteration, then total. Node, we're gonna pop that off the front of our queue. So, and then remove it, so remove it. And then we're gonna save it to our temporary level. And then we're going to add its non-null children. Well, it has a 9 and a 20. 9 and 20. That is the end of this level. So what do? We push the things onto our output. So return is got a 3 on it now. All right, next iteration of the loop, level clears. What do? Well, the size of our queue is now 2, so there's going to be 2 iterations. So 9 and 20. And a comma, so that there's going to be 2 things on the level. So the first thing, pop the front of our, so pop this 9 off, and then we're going to add its value to the first position. That's a 9. And then we're going to add its non-null children to the queue, which it has none. And then next iteration of the for loop is a 20, so we're going to pop it off. And then add it to our level. It's at 20 there. Add its non-null children to the queue, so 15 and then 7. 15, 7. And then that was our 2 iterations, so we're going to end there and push that level onto our output. So 9 and 20. All right, level clears because we're on to the next iteration of our outer loop. The size is again 2 so the size of the queue, so 15 and 7, that's 2 things. So we're going to do 2 iterations of this inner loop. Pop the first thing off our queue, that's a 15. Add it to our temporary level, 15. Add its non-null children, there are none. Next iteration, it's a 7. Take that off the front of our queue. Add it to our level, 7. Add its non-null children, there are none. So then we're at the end of that for loop. We're going to add that to our output. So 15 and 7. And then we're going to check our queue is now empty because we've added nothing to it. So we're going to break out of all this and then return. We're going to return 3, 9, and 20, 15, and 7. 3, 9, and 20, 15, 7. Cool. That is our expected output. And then I think that's pretty much it. So I'm going to go ahead and give it a run for syntax errors. Did I miss anything? Is there anything else I wanted to mention? Level wise, so this inner for loop of exactly the number of elements in the queue at that particular time, that's how you do traversal by across level by level, frontier by frontier. Talked about space complexity and time complexity, and we did an example. All right, let's go ahead and submit it. Cool. All right, now we can mark it off. Thanks, guys.